Hello, this is ME490 Sustainable Energy Applications. My name is Abdallah Ghazali and I'll be presenting the FRAD term in the energy balance equation. For the agenda, I'll provide some background information, then give an overview of the method used to calculate FRAD, and finally share my results. For the background, it's important to understand that radiation travels through electromagnetic waves. Whenever an electromagnetic wave hits a surface, there are three options. It can be reflected, it can be absorbed, and it can be transmitted. The transmitted portion plus the absorbed portion plus the reflected portion has to sum up to the incident portion. In other words, IO must equal IA plus IT plus IR. For the methodology section, we need to understand what FRAD signifies. FRAD is the fraction of solar energy input lost due to radiation. In other words, we can write FRAD as QRAD over QSOL. Let's define these two terms individually. QRAD is epsilon sigma AT to the 4, where epsilon is the emissivity and it's a property of the material. We're going to come back to this term later. Sigma is the Stefan-Boltzmann constant and it's 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the 4. T is the absolute temperature in Kelvin. A is the surface or radiating area and usually in units of meters squared. The other term that we have is QSOL and it's CIA, where C is the concentration ratio measured in number of suns and I is the nominal direct normal irradiance. For this problem, we're going to assume 1000 watts per meter squared for D and I. Coming back to that emissivity term, we have to introduce a black body. A black body is a body that emits all the electromagnetic wave traveling through. So it's the best case, it's the ideal case to have. We're going to assume this ideality in this problem and give epsilon a value of 1. Putting things together back in our original equation and plugging the definitions of QRAD and QSOL and plugging epsilon equals 1, we see that the areas cancel out. And finally, we get this final equation to calculate FRAD, sigma T to the 4 over Ci. This is the final equation that we'll be using to quantify FRAD at given temperatures. Plotting FRAD against temperature, we get this trend. It's an exponential trend at two different concentration ratios. The blue curve is for 1000 suns and the red curve is for 3000 suns. These two curves make sense because if we go back to that original equation FRAD, we see that FRAD is a function of temperature raised to the power of 4. Since sigma, C, and I are all constants, as we increase temperature by a factor of 2, FRAD gets increased by a factor of 16. So the results make sense. As a side note, if we were to calculate the receiver efficiency, we use this equation, 1 minus FRAD. One last thing to note is, we have a special case when QSOL equals QRAD. When that's the case, FRAD equals 1. So if you plug in the definitions of QSOL and QRAD and solve for temperature, we get this special case, special temperature. This temperature is known as the stagnation temperature. It's the temperature at which all the solar energy input gets lost due to radiation. It's also the maximum temperature that could be achieved by any receiver. To extract the stagnation temperatures from the plot, we use the interpolation command in MATLAB. At FRAD equals 1, we hit the curves and we come down and we find a stagnation temperature of about 2050 Kelvin at 1000 suns and a stagnation temperature of about 2700 Kelvin at 3000 suns. It's important to note the scales used in this problem. Notice that this equation doesn't have any limits on the x-axis scale and the y-axis scale. The x-axis scale being the temperature scale and the y-axis scale being the FRAD scale. So technically, the temperature scale could go up to infinity and the loss fraction scale could also go up to infinity. However, we're not interested in that. We're only interested in the region where the loss fraction is between 0 and 1 because that's the region that makes sense to us. If we have loss fractions greater than 1, it means that there is more energy that's being radiated than what's actually coming in, which doesn't make any sense. Similarly, in the temperature range, we already said that the stagnation temperature for a given concentration ratio is the maximum. So for these two cases, we got a maximum temperature of about 2700. So we're not going to achieve more than that. So it doesn't matter whether we included more temperatures than that, it's not going to help us in any way. So it's important to say that this temperature range represents the applicable range for these two cases in this given problem. Similarly, it's important to only include loss fractions between 0 and 1.